Thank you very much. And greetings, everyone. I'm going to talk a little about modern transport problems. Quickly about myself. I work at Kaspersky Lab at Security Assessment Department. We are responsible for all pen testing and auditing projects that are done by Kaspersky, and I'm a reverse engineer in this department. My job is strongly connected with industrial control systems, Internet of Things, and some other things. And occasionally, I have a chance to look through different areas of modern electronics in search of something new and interesting, and sometimes this results in the things I'm going to discuss in the next 40 minutes. Well, all of you may have heard that all good combustion engines are not in the best shape in people's minds. This is caused by such events as Dieselgate, you may have heard about it, and some other negative information in the mass media. And the alternative the market is offering now are electric vehicles, or EVs in shortened form. And that is making them interesting for security researchers. We are not the exception. So things that can be researched include as EVs themselves, as various infrastructure devices. And when we started to look what can we research, I really had my eye on this BMW i8, but it wasn't acceptable, so we started to looking for something small and maybe cheaper, and now I will present you a personal charging station research. And when I'm saying personal, I mean that this station is going to be developed for installations at private homes, so there won't be any payment system. So there are a lot of vendors in that area now, and every vendor has its own piece of market. There is no well-recognizable leader. We were looking for something interesting, so at least we need a station with some kind of network interface or something like that. And we found out that some vendors are trying to attract more customers' attention by implementing remoting monitoring and controlling feature. That means that with that station, you will be able to start and stop charging your car with the mobile application with your smartphone. And that is why we started to look in that direction. And so finally, here is our hero. ChargePoint home station by ChargePoint Incorporated. And you can see from that diagram that they have a really good, ambitious for growth. And the reason why we chose exactly that vendor, so that is their marketing style. So we believed that guys who created this picture are not able to make anything boring. By the way, this is a picture of different socket types, so those sockets that connect your vehicle and your charging station. There is some functional scheme of charging station. It is always based on some kind of a smart relay, which is responsible for accommodating the charging current on and off, or turning the charging current on and off depending on external conditions. For that station, several communication channel exists. The first I'm going to talk about is vehicle communication channel. It can be implemented in several ways, starting from simple one-pin interface, which car present pin, and ending with a dedicated CAN bus, which can offer great abilities to talk with vehicle internal systems. There is always some backend connection exists, which usually takes place over Wi-Fi or wired connection, and several protocols exist now for that purpose, and the most well-known is called OCPP, or Open Charge Point Protocol. For stations that are installed in public places, there is always NFC present, so for this wireless interface for payment system implementation, but as I said before, we did our research on a personal station, so this interface is out of our scope now. And of course, several more interfaces may exist depending on the device design. And in our case, this is a Bluetooth interface, and it is used at certain moments for communication with the smartphone. First, let's have a look at this mobile application, which is used for controlling the charging process. First, I need to mention that our charging station can be in two different states. The first state is inactivated state, and during that state, only the Bluetooth interface is available. And this Bluetooth interface is used for Wi-Fi connection settings and establishment the connection to the backend for further controlling. And after connecting to the backend, the device is entering the activated state, and at this state, the Bluetooth is disabled, and the device receiving all commands over Wi-Fi. The first state is more interesting for us this time because it invokes direct communications between the app and the device. So let's see what we can find and learn about that Bluetooth channel. We are using Android smartphone, and Android kernel is allowing us to make a dump of all traffic that is passed over Bluetooth. It can be done with the HCI dump tool, and collected logs, collected data can be further analyzed via Wireshark because it supports the HCI dump format. We activated our stations and made a dump of all communications that took place between the device and the phone. So we realized that there is a simple RFCOM protocol implemented, which means that it's just a single UART line that commutates over the air via Bluetooth, and all commands have text format. Here is the list of all commands, and the most interesting for us started with number 3. So these two commands, number 3 and number 4, are used for connection to the Wi-Fi network. So with these commands, you are passing your Wi-Fi network parameters. The 5th command is used for establishing those connections to the backend server. So after processing that command, your device will be online and will be able to receive all remote commands from the vendor side. And the last command here is shut down Bluetooth. This command, as no surprise, disables the Bluetooth service, and that's finishing transaction to the activated state. Now, let's have a little bit closer look at the device source code. It is written in Java, so we can decompile it. And we found those activity, which is called ResetToFactoryDefaultsActivity. And what is interesting here, and you can see those lines like flash sequence and request camera permissions. So this code is probably appeals to the camera's flash. So that sounds interesting. And you can also see this screen picture, which shows how to possess your device in front of how to possess your smartphone in front of the device. So now I'm going to show you a very small video that will show how this function works. So here you can see the smartphone and the device. Here are two small windows in those places. We can activate this activity by setting the start button, and so that is how they implement this function. You can see those blinking, and you can see that the device accepted our blinking by those red light. So, by the way, this is really just a factory reset function. So this is the same function that is usually implemented in your home router via this small reset button. But the way how it is implemented here shows that developers use their fantasy not only for drawing those funny pictures of sockets. Now we're switching our focus. We're finishing with the mobile app, and we're switching our focus to the charging station itself. First, let's look which services are available to us from the Wi-Fi network. And here is a small table of these services. There are not so much, only 3 of them. The first is Telnet on 23rd port. And also there are 2 SSL services. One of them is probably HTTPS, as no surprise, on 443 port. And the second, at this point, we don't know because it can be anything. So we try to use some default credentials, but none of them that we were able to think about was accepted by the device. And what about SSL? It is set up for mutual authentication, so we need a certificate to communicate, to talk with it, and now we don't have one. So let's have a look inside the device, and maybe we will find something interesting here. Here is how the device looks like if you will unscrew this front panel. It consists of 2 boards, 2 separate boards. One of them is power board, and there are a lot of elements as coils and relays that are here for accommodating big charging currents. And the second board is called Panda board, and it is called so by the developers. They wrote this small string in the top side of the board. Now let's have a little bit closer look at both boards. On the power board, as I said before, there are a lot of components that are responsible for big currents commutations, like those strips for connecting the charging station to the vehicle and to the electrical grid. Also there is that mechanical relay for commutating big AC currents. This board is controlled by separate MCU, which has, here it is, it has MSP 430 architecture. This is a proprietary architecture by Texas Instruments, but anyway, all specs on it are available online. And finally, there is a small socket, proprietary socket that connects 2 boards together. We didn't spend much time on this board because, we were more interested in network communications, and it is a responsibility of the Panda board. So I'm going to continue to the Panda board. Here it is at a closer look. It is based on Atmel CPU with an ARM architecture. It is here with number 1. Also, there is some additional chips for this controller to work like NAND chip and RAM chip. In addition, there is those extension board which is developed by ISM and which implements all wireless interfaces. It can operates with Wi-Fi, with Bluetooth, and even with NFC. So the vendor is probably using the same hardware design for different stations, even for public stations. And finally, there is a small debug socket on number 3. And we were able to find a JTAG interface on this socket, and JTAG interface is always a good start for hardware research. Couple of words about tools that we were using. First, this little pin board is called JTAGulator, and it is used for determining JTAG pinout. It works rather simple, so you're just connecting it to the socket you suspect that have a JTAG, and if you are right, it will show you the exactly pins that are used by these protocols. And that small red board is our programmator. We are using it in pair with OpenOCD. OpenOCD is a well-known and widely used framework that is responsible for setting breakpoints, via JTAG reading and writing memory, all of that debugging stuff. So, to understand how the device operates, we now need to get firmware from the NAND memory. And of course, there is an option to chip out the NAND, but it can be very harmful to the device, and we now don't want to break anything before all the fun begins. So to read it in some other way is a great idea, and it can be done with JTAG. NAND data lines are not connected to the CPU core together, so they cannot be read simply by setting address and reading the data from that address. There are some special scripts that are included in the OpenOS distributive that are responsible for reading NAND with different controllers, but unfortunately none of them was acceptable to our controller. Even some of them were developed for Atmel. Everyone failed, but we did it another way. So here you can see the sequence of all bootloaders that our charging station passes through during the boot process, and we found a function that read NAND at the lowest level bootloader, which is called bootrom, and by means of JTAG we are able to invoke it in cycle so that we can read all NAND content first to the buffer in the memory, and then in the operative memory, and then to read it to the host. Here is a table that shows us the structure of those NAND content. The most notable here, we can see two Linux images. So if one of these images will be corrupted, the device will be able to boot from another one. Every image contains of U-boot bootloader, kernel arguments section, kernel, rootfs, and the parameter section. The parameter section is the most interesting here. It is a section with a proprietary format, and it contains, as no surprise, several device parameters like MAC address and serial number, and among other, there are several certificates. So that's look interesting for us, and maybe we'll look at them sometimes later. And in addition to those Linux images, there is a section that is called SSH key recovery partition, and I will discuss it a little bit later too. By the way, there is one other thing that can make our life easier, and that can be done by means of JTAG. So this is the Telnet access, and with it we will be able to debug separate processes and not whole system as it is done now by JTAG. As soon as now we have all NAND content, we also have this shadow file, but the shadow file contains strong hashes. They use MD5 with salt, so we want this is a secure algorithm, and we weren't able to break it by means of brute forcing. But from the other hand, now we can analyze those binaries that is responsible for validating user login and password, and after that we can find it by means of JTAG again in memory and patch those instructions. Originally this is conditional branch, and if we patch it, and if we change it to unconditional branch, every password will become correct. So that's how we did it. Now we have a JTAG access, and now I'm going to continue with the network interface, and I'm going to start with those two SSL services. Okay, we realized that upper SSL service, which is at those ports which started with 5555, it is a Telnet, encrypted Telnet service, but this is exactly the same Telnet as we already have access to, so it is not interesting for us at this point. And the second port number 443 is, as no surprise, HTTPS. It is used for common gateway interface, so we can invoke some binaries with it. And SSL layer for both these two services is implemented via SSL with mutual authentication. So to be able, as I said before, to be able to establish the connection, we need a certificate. So let's start our search from those certificates we found in the parameter sections. There are two certificates. Okay, one of them is ca.crt certificate, which is certificate authority and is used for client certificate validation. And second is system.crt certificate. It is a SSL server certificate. So it is stored with a private key, but private key is encrypted. But all the data that is needed for that key decryption is available at the parameter section, so we're now able to get it in the clear form. That is one of the way how it can be done, and the way how we did it actually. So there is those code in this tunnel which derives the passphrase for the key decryption from several, exactly three files from parameter section. One of them is system MAC address, and 2 seconds are like special additional data. We have a JTAG, so we can put the breakpoint at the end of those code fragment and download the decryption key after this code executed. So when I learned about JTAG, and I became really lazy with this kind of tasks, because I don't want to even to know the algorithm that is used. It is something that is based on exclusive for, but so it is not really secure, not really interesting. So now we're having the certificate with its private key, and we know that it was created somewhere on the vendor side. So why shouldn't we try to use it to establish the connection to the SSL service? So we tried, and bingo, it works. So don't be afraid of those red screen, of course, because there is no actual web content on the device. And now we are already able to access a common gateway interface. Now let's try to figure out why this is possible. So why it was possible to establish those connections with those certificate, this connection with this certificate. Here are 2 certificates at a closer look. Several fields of those certificates. And what is notable here is that system.crt certificate is signed with that CA certificate. You can see that from these serial numbers that are written in bold here. And in this signature is checked during certificate validation, but in the web world, not only the signature is checked, but of course the subject field. So those fields that is showed who the certificate was issued for. But in the embedded world, things are working in a very specific way sometimes. So that is that case, and that is why the certificates works. Now we can proceed to the HTTP part, and there are 3 ELF files that can be invoked with it. This is some form of debug interface, and running forward, I can say that the vendor removed those HTTPS server from the device at the latest firmware. There are 3 binaries. The first binary is called upload.sm, and it is used for uploading different configuration files like payment system configuration. The second is download log.sm. It is used for downloading different types of logs from the device, like web server log or system log. And the last one is get server, and it is used for issuing different debug commands. So we didn't find any charging control commands in this binary, but for example, there is a reboot command available, so it is still can be interesting to play with it. As for input format of the input parameters for upload the same, it is just the file name that is passed to the HTTPS server, and for two other, there is a specific command format. It looks like a simple text line which consists of tokens that are separated by the pipe symbol. The first token is always same DTAG. In this example, this is RBT, and all other tokens represent different command parameters, like charger serial number, timestamp, some command-specific parameters, and so on. One of our purposes was to find vulnerabilities. So here are findings in this CGI interface. There are some loopholes in the input verification in upload the same binary, and that leads to arbitrary file write vulnerability. You can see from that little code snippet that they just pass the substring from the input to the fopen function without proper verification of that // well-known sample sequence. So we can overwrite not only files with settings, but any file in the system, by the way, for example, including shadow file, binary files, library files. So that can be dangerous. Also, as input is not verified in this upload the same binary, there is also OS command injection vulnerability exists, but I need to note that all OS commands here will be executed with very low level privileges, and the system is designed in that way so that mostly objects require root access, so we won't be able to do anything with that commands. And finally, there are two series of stack buffer overflow vulnerabilities at the last two binaries, which is download log SM and get server. This vulnerability could lead to remote code execution, and it is caused by using of that type scanf function for parsing those specific commands. And you can see that it is just reading tokens to the different buffers, and if the buffer is on the stack and no length verification is performed, there can be an overflow. A couple of notes about exploitation of that stack buffer overflows. Here, the kernel with address space randomization is used, so stack position is randomized from the one hand, but from the other hand, the stack is executable, so we still can be able to execute our payload code from it. In this case, we can call a vulnerable binary that is part of CGI interface multiple times, and when binary fails and it always, of course, will fail due to payload with wrong stack address. It won't affect the other parts of the system, and even if we send the payload that is compiled for the exact stack address, there always be a probability that the exploitation will succeed. Small probability, by the way. But there is a big number law, and which states that with more and more tries, the success probability becomes much greater. So here are some details for our particular case. Stack here can be placed in 512 different positions, and the big number law says that we will need 315 tries to guess position with 15% probability. We found that the web server operates correctly when we are issuing 2 seconds, one request per 2 seconds. So we need 2 seconds per one exploitation try, and that leads that after 15 minutes from the beginning of the attack, we in average, we will take control over the device, and this time still can be practical. Now I'm going to tell what we learned about network servers that is responsible for communications with the backend. It is the protocol that is implemented here is implemented over HTTP and WebSockets, and it is called OCPP 2.0 during the connection establishment. This protocol actually exists now, but the problem here is that it was published on 12th April this year, and this investigated firmware was released several months earlier. And in addition, our vendor, ChargePoint Incorporated, is not the participant of the organization which is called OCA and which is responsible for those protocol development. So those name is looking strange for us at this point. And further investigations shows that what vendor did is they took previous version of that OCPP protocol, which is OCPP 1.6, and they created their own protocol on its base. So OCPP 1.6 protocol is often criticized by information security community due to lack of attention for security problems. For example, this protocol doesn't provide any encryption for data transmission. And here, this new version of protocol is implemented over HTTPS, so it uses TLS, and so it is encrypted. And this is a really good and big step forward from the previous version. Let's have a closer look at the vulnerabilities again. So in this protocol implementation, it is always the same. This is always the same vulnerability as was in common gateway interface. It is caused. This is stack buffer overflow, and it is caused by using of the same type of scanf function. But now the process that is responsible for this protocol is not a part of CGI, so it may seem that we are not able to, to try to exploit to execute our payload multiple times. But the problem here is that there is a very specific approach that I usually see in different industrial control systems, and it lays in the fact that every critical process is tracked for fails, and it is restarted after fails. So it can improve the system resilience against different kinds of denial of service attacks, but it is a terrible anti-pattern from many other points of view, and our examples show this perfectly. So we're still able to make this repeated exploitation attack. And here are some details. So this time, much bigger time delays must be made. So now average attack time is 6 hours, which is much bigger but still acceptable. But the problem here is that there will be a station reboot every 4 process restarting, and during this station reboot there will be diode blinkings in the front panel of the device, so this can attract a lot of undesirable attention to the attack, and this vulnerability in CGI is still more practical for real attack. Now I'm actually going back to the presentation title. I promised you to show the way to the vendor's network, and so here is now it is the time. There is a process that is called sshrevtunnel.sh. It is actually a bash script, and you can see some code snippet from there. And what this code does. It tries to establish remote SSH connection to the server that is located somewhere at the vendor side, and authentication is done with SSH key, which is stored in the device SSH recovery section in clear form. So this is probably some kind of a specific debug backdoor. This remote backend server is called mothership in one of these script comments. So developers were maybe big fans of Star Wars or Star Trek, but anyway, there is an opportunity to connect to this backend, to this mothership, and to test all these swarm control features. Of course, we didn't do that, but that can cause some serial problems, if the researcher will be more greedy and less responsible. Now I'm going to talk a little about Bluetooth interface, but very little, by the way, because the usage of this interface is very limited. As I said before, there is a scheme of implemented Bluetooth stack, and I think the most notable here, we didn't find anything interesting in those upper layers, but what is interesting here is that they implement Bluetooth HCI level over UART. So that is very unuseful for modern electronic devices. Now this host controller interface or HCI interface is usually implemented over USB, which is done in your laptops, or it also can be a part of system on chip, which is done in smartphones. And the only device we were able to Google during our research with the same HCI interface of UART was some very old Sony Smart TV, and these facts, I think, are making this type of interface some kind of guest from the previous era at which IoT devices didn't attract so much attention from the security community, and this is why this interface may have some, childhood diseases maybe in it. Unfortunately, we didn't have enough time to look so close in one particular interface, but that can be an area for further research. Couple of words about vehicle interface. In our station, there is a specific socket type. It was drawn on these funny pictures. It is called J1772, and vehicle interface here is implemented with only one pin, which is called control pilot. And the vehicle reports its states to the charger by changing the resistance between this pin and the ground. There can be 3 available states for the vehicle: ready for charging, charged, and ready for charging with ventilation. So, as I said, we didn't and still don't have electric vehicle in our lab, so we emulated those different states by means of resistors, how it is shown on this little picture. Couple of words about communications with the vendor. So at the end of our research, we sent all our findings to ChargePoint Incorporated. It was on 7th of August this year, and the vendor showed his commitment to securing his devices and coordinate with security community. They reacted quick enough. So after we discussed all vulnerabilities in more details, they made a mitigation plan on 21st August, and finally the firmware with all bugs fixed, all fixes was released at 14th of September. This is a slide which ChargePoint Incorporated sent to us So they wrote it by themselves, and you can read there that it was, by the way, the first time they received some security issues from the third side. So, and that's, I think that is making the reaction speed even more respectable. Couple of words in conclusion. Okay, so as I said before, all vulnerabilities were patched, and what is, I think, the most awesome in this charging station is the firmware upgrade system. So every station that is connected to the backend will receive firmware update automatically without any user interaction. So we can be quite sure that all devices are already patched. And about future plans, you know, EV industry opens a great area for further research. And this includes transaction protocols. And what is the most interesting, I think, for me are those protocols that are used for communication between the charging station and the vehicle, because as I mentioned, that can be a CAN bus, and CAN bus can open a really wide road to the vehicle, internals to the vehicle network. That is all for today. Thank you very much for your attention, and your questions are welcomed.
Thank you. You have questions? Okay, we'll start from...
I think this man was first. So.
Then we'll go there, and then we'll come here in the front.
Okay, so did a vendor ask you to find vulnerabilities, or did you start to find them by yourself?
So by the way, we started it by ourselves, but we, as I said before, we were really cooperative to the vendor, so we sent our first email very quick.
Okay, thank you.
Okay.
We'll go to the back and we'll come, okay? We're trying to take it in the order of the, okay?
Thank you for your presentation. You showed the buffer overflow code. So it was very exact C code. How did you get it? You made white box testing, or?
You mean the first or the second?
The second, where the length was not specified, but it was rather well formatted.
Okay, the second was found with some form of vendor help, because they weren't able to communicate with the, so as I said, there is an SSL implementation, but they helped us to connect, to imitate the server. Yes, it was a white box.
Okay, thank you.
Thank you. We have a question here in the first row, and then we'll be going back to you, and then we're going to the middle, okay? Right here. Not sure. Okay. Yes, you raised it first.
So you mentioned that the Panda boards are reused in ChargePoint's commercial chargers as well.
Sure.
My question would have been if you found any of these charge points publicly exposed on the internet.
No, and we haven't even tried, so this wasn't our target at this time, but maybe we will do it in future.
Yeah. So, yeah, you mentioned about Bluetooth. Bluetooth, right? So is it works on 2.0 or 4.0 BLE, or what exactly it is?
Can you please repeat your question? I didn't catch
you
it.
mentioned about the Bluetooth communication, which
Bluetooth, yes.
between mobile and your the
Yeah,
AV
Bluetooth
charger.
4.0.
4.0.
Yes.
And you sniff with the BT Snoof, which is in Android mobile, right?
With HCI dump. We made HCI dump.
Yes.
Not BT Snoof.
Okay, okay. Yeah.
Thank you. We'll take the question from you. There. Raise your hand, please. Okay, perfect.
were all types of chargers affected, or just some particular cases?
This was not loud enough. Please repeat.
Were all types of chargers affected by those vulnerabilities?
You mean all chargers, all ChargePoint stations, all
Yeah,
ChargePoint host stations?
Yes.
Yes, they were, because these are vulnerabilities in one particular firmware version. So, but only we can be sure only about, this model. So there are some other models that are made by ChargePoint, and I can't say anything about them. I understood you right. Yes.
All right. Thank you.
Thank you. And then we have there 2 questions, and you'll be the last one, okay?
You specified that after having the certificate, you could communicate with a device and exploit it with its wireless interface.
Yes.
So, having the certificate, can you exploit it over the internet or only in its on a local network?
Only over local network, of course.
So it doesn't.
So we are not able to do it over internet because, as I said, we made only one. We were focused only on this station, on the local one.
Oh, okay. I see. Thank you.
Thank you.
Just one short question. Did the vendor pay?
No.
No?
No.
Thank you. And our last question for this session will be right here. Please raise your hand. And for any other questions, I will invite you to have a talk after with Dimitri.
Hello. Just want to ask, how did you solve the vulnerability related with the JTAG? You said that most of the vulnerability, they are starting from the JTAG connector. So as far as having the interface one JTAG, so you can still connect, how can we solve this? I don't know if you understand.
No, I didn't understand the question.
About the JTAG connector.
Okay, JTAG connector, well.
Is the start of many vulnerabilities, because through this port you can access the device.
Yes.
So how could you solve it? Physically remove it, yes, but after that you can still connect to the pins on the microprocessor, or the JTAG is internally connected. It's more difficult, but it's still possible. So how can you protect against JTAG attacks?
Oh, okay, I understand your question now. And
thank you.
Yes, it is possible to protect against JTAG can be blocked. So there is a possibility to block the JTAG in some chips, but in fact, I think I haven't ever seen the exact device where this possibility was implemented. So now it is used. It is not used, in fact.
Okay, thank you.
Everyone, thank you for your amazing questions. Dimitri, thank you for your presentation.
You're welcome.